Okay, so January 27th, let's take a look at test number 1. Take a look here. I've got some of the right answers, and hopefully you got them as well. So question 1 was E, question 2 was A, question 3 was B, question 4, the correct answer is carbonate. So unfortunately for the second one, I made a typo and I had NH3 on your test, and I've corrected that to NH4. If you had ammonia, which is NH3, I accepted that as correct. So water is less dense when frozen. Hopefully that's obvious because ice cubes do float, and this is due to the formation of hydrogen bonds. And there we go. Water scarcity can be both due to physical and economic reasons, so that was right out of the lecture notes. And water licenses, you need to say something about that they're given to control the amount and uses of water for various purposes for 1 mark. So true or false? So false, true, false, false, true, true. C was on white zone and green zone. So this is 2 marks, which means you didn't have to necessarily have all of this, but I wanted you to talk about green zones being unsettled and mostly crown land, and white zones being more settled or privately owned land. And you could talk about some of the different uses or the authority to set regulations, but didn't expect everything for the full 2 marks, but a little bit of a decent description on what each of these things mean in terms of regulation in Alberta. So let's take a look at the calculations. So first one here is hopefully straightforward. Basically chemistry 101, you have the number of moles and you have the volume. So you have 0.25 moles. Convert that to grams by multiplying by the molecular mass and you get 14.61 grams. Number 16 is again just basic formula crunching. So the mass per volume formula is there. It's the mass of solute over the total volume in milliliters, which is grams over grams, times 100 to get a percent. So 39 divided by 355 times 100 equals 10.99%. Number 17. So 2 parts of this. First is converting to parts per million, parts per billion to parts per million. This is a conversion factor. You divide your parts per billion divided by 1,000 and get 0.35. And of course, parts per million are milligrams per liter. So we can rearrange this formula here and we get milligrams is equal to the parts per million times the volume. So 0.35 times 20,000 liters, that should say 20,000, is equal to 7,000 milligrams, which of course or divide that by 1,000 to get 7 grams. I think some people messed up the conversion between milligrams and grams, believe it or not. Okay, last one is talking about arsenic in water, and the lab analysis came out as milliequivalents. So there's the value there, and we need to convert that to milligrams per liter to see if that is okay with Health Canada. So in order to do that, you take the milligrams per liter, you multiply the milliequivalents per liter times the equivalent weight, and our final answer is 0.008 milligrams per liter. So that is a little bit less than 0.01 milligrams per liter, which means yes, the water is acceptable for drinking. So hopefully you did well on the first test. If not, if you have any questions, you can always consult with me at any time, and we will move on. That's worth 10%. So each of the tests are worth 10%. So if you didn't do so well on this one, you have 3 more chances to boost your markup. So let us go to today's lecture, and we're talking mostly about hardness today. So we talked about last day hardness being mostly due to calcium and magnesium. Sometimes these other ions come into consideration, and but they're usually not that significant. And you'll see with one of the sample questions, we'll have iron in there, and it's like the third or fourth decimal place. So this is our water classification, and one thing that I wanted to make note of is this here. So water hardness is classified as milligrams per liter of calcium carbonate. And that's kind of a historical thing in that it used to believe that water hardness was all from calcium carbonate. And so those were the units. Of course, now we have other sources of calcium, and of course we have magnesium as well. But the units have stuck, and so we still use them. So here's a sample question. And we can do this one right here on the side. So to calculate hardness, there's 3 steps. And the first step is we need to convert the amount of calcium here and the amount of magnesium to milliequivalents. So that's the first step. So we'll make some notes here on the right-hand side. So determining hardness. So about 3 steps depending on how you count it. So step number 1 is convert to milliequivalents. So convert the concentrations of calcium and magnesium to milliequivalents per liter. So we can do that, and we'll do calcium first. So calcium. So remember, to convert to milliequivalents per liter, you're going to take your milligrams per liter and you're going to divide by the equivalent weight. So in this case, we have 17 milligrams per liter, and that's divided by 20 milligrams per milliequivalent, and I get 0.85. So 0.85. And if you take a look, my milligrams cancel out. So milligram cancels out here, and I get milliequivalent per liter. So we'll do the magnesium. And the magnesium is 8. I'm not going to write all the units this time. 8 divided by 12.2. So in this case here, I get 0.65. 0.65 milliequivalent per liter. Okay, so step 2. Step 2 is add up the hardness. So add up the calcium and magnesium. Okay, so that's, of course, 0.85 plus 0.65, and that equals, is that 1.5 milliequivalents per liter. Okay, so step 3, I'm going to squeeze in over here on the left. Step 3 is convert to the proper units, which is milligrams per liter of calcium carbonate. Calcium carbonate. So to convert that, we have the milliequivalents per liter. All right, so that's 1.5 milliequivalents per liter. And we multiply that by the equivalent weight, which is right here. So 50 milligrams per milliequivalent. So the answer there, 1.5 times 50, is of course 75 milligrams per liter calcium carbonate. So sorry about just cramming everything in here. Sometimes it gets a little bit squishy. You can see that that does correspond to what I see down here in my answer from done before. I found this online tool Right here you can see this link, you can check it out, and you can punch those numbers in and it does it all for you, and it comes down with 75.3 something and confirms my answers. So I have another sample coming up, so we'll do another one and we'll do more next day as well, just to give us lots of practice. So here's another one, sample calculation. So remember, step one is basically converting everything to milliequivalents. So we'll do that all over again. We got calcium. Remember what you do is you take the amount of calcium, milligrams per liter, divided by the equivalent weight. So 20 milligrams per mil equivalent. That one I can do in my head, which is 2.0 mil equivalents per liter. Magnesium. So magnesium, we have 10. I'm not going to write all the units this time around. 10 divided by 12.2. And I feel like I got a calculator here somewhere. 10 divided by 12.2 is 0.82. 0.82 mil equivalent per liter. And notice in this case here, I do have some iron up there. So let's do the iron. Okay, so the iron is 0.1. Notice it's a very small number divided by 27.9. So the iron is 0.1 divided by 27.9. You're going to see it's a very, very small number, and it is 0.0036 milliequivalent per liter. So sorry about my handwriting. It's not so easy writing on the computer screen. So number two is we add up all the hardness. So number two, that means we got 2 plus 0.82 plus 0.0036. Okay, so we can add all that up and we're going to get a number. So 2 plus 0.82, I guess I could have done this in my head, 0.0036, right? So it's 2.8236. Probably not perfectly accurate, and then I didn't carry any significant digits down for the magnesium past the 2. But the answer there is milliequivalent per liter. And 3 is you're converting to the milligrams per liter of calcium carbonate. So we need to convert that back and multiply that by the equivalent weight of calcium carbonate. So multiply that, and that's the equivalent weight isn't on there, but we know it from the previous slide, which is 50. And that's 50 milligrams per milliequivalent. And so the answer here times 50 is I get 141. 141 milligrams per liter calcium carbonate. So it's slightly different from the answer that I have down here, 140. It's possible when I did this before I rounded somewhere, and that's what gave me that answer. So that's how you do hardness. And like I said, we will come back to this and do some more sample problems later in next lecture. So that being said, for test number 2, you're going to get a water analysis question, and there's going to be a whole bunch of things you're going to need to do for that. So you can see some of the things we did before, converting everything to milliequivalent per liter. You're going to draw a bar graph, maybe figure out the percent difference between anions and cations, list hypothetical combinations. You're going to calculate hardness. And the last thing you're going to do is calculate alkalinity, and we haven't talked about that yet. We're not going to get to it today. We're going to talk about acidity, and we'll talk about alkalinity next day. So on the topic of hardness, just wanted to talk about today's or last week's lab. And last week's lab, you were measuring calcium and magnesium by doing titration. So EDTA is something, it's actually found in shampoo. And for that reason, it takes away the calcium and magnesium and makes the water softer. So this is a 1-to-1 reaction. And you can do a titration with EDTA and colorimetric agent, and that way you can measure exactly how many ions of calcium magnesium are in that solution. So there's just another diagram showing the EDTA forming this complex around the divalent cations. So this is apparently what it's supposed to look like. I've never seen it this dark. It starts off with red and then turns blue. And this is in fact the color, probably the darkest colors I've ever seen in the chemistry lab. Most semesters they're not quite as dark, but you can see it's going from red to blue. So let's talk about acidity and alkalinity. So you probably know that water itself is a weak acid, meaning it can break down into hydrogen and hydroxide ions. And so that does that so in a 1-to-1 ratio. And in pure water, which is a neutral pH, the hydrogen ion concentration is 10 to the minus 7 moles per liter. So that's a good number to know because that's neutral, and knowing what neutral is good. So often we don't talk as much about the hydroxide, we talk more about the hydrogen ion concentration. And a term used to describe that is something called the pH. So 10 to the minus 7, you know, we don't really necessarily like to think about exponent numbers all the time. They're kind of awkward to work with. So we convert things to a pH. So a pH is the negative log of the hydrogen ion concentration. So we'll do some sample calculations in a minute. But if you remember that neutral water is pH of 10 to the minus 7, so a pH of 10 to the minus 7, you can punch that in your calculator and what you get is a 7. So this is called a neutral pH. So it says here, why are pH measurements important? Because so many things are going to depend on pH. When water is too acidic or too alkaline, it can be very reactive, it can corrode pipes, it can kill fish, it can do all sorts of things. So it's important sometimes to have a neutral pH, or for some processes you want it more acidic than alkaline, or sometimes more alkaline than acidic. So pH comes up in many, many places. So there's the pH scale and some of the things that you might encounter out there. You can see, for example, a lot of beverages are up at the top there. So Coca-Cola is around 2 or 3, and tomato juice maybe less acidic, around a 4 or 5. And you can see that on here as well, it's talking about fish. And so, like I said, if your pH is off, you can be killing wildlife. Up at the higher end of the pH scale, we have things like baking soda and seawater and all sorts of different detergents and other things like that. And neutral, of course, is right here at pH 7. So let's try some sample calculations. I want you to be familiar with that formula of pH. So here's the formula, right? And so we'll do number 1 over here. pH equals minus log of the hydrogen ion concentration. So for number 1, it's just punching into this formula. And everybody's calculator is a little bit different, so I encourage you to take a good look at your calculator, make sure you understand how to do this for these calculations. So it looks something like that. So in my calculator, I punch in the number and then I press log. In some calculators, it's the other way around. You press log and then punch in the number. But I'm going to do that right now. And I get, when I press log, I get minus 2.6, but of course there's a minus sign out front. So the answer here is, of course, 2.6. So notice here, the exponent is -3. So I know that it's going to be close to 3. So it's going to be 3 point something or 2 point something, right? And so that's always a clue that I'm on the right track. So for question 2, we're doing the opposite. So for question 2, we're going to take this formula and we're going to rearrange it. So if you know how logs work, then the inverse of a log is an exponent. So basically what it does is it looks like this. So it's 10 to the negative pH. Now there's different ways to do this on different calculators. Again, if you have some issues with your calculator, please let me know. So in this case here, I'm going to put 10 to the minus 6.2, and I can actually punch that into my calculator just like that. So let's see here, we've got 6.2 negative, and I can go shift log, and so I get 6.3 times 10 to the minus 7. And of course that has units, which is moles per liter, so a big M. Okay, so for question 3, it's asking us how many times more acidic is lemon juice than orange juice. So what I'm going to do is convert each of these to concentrations. So I'm going to use the same formula that I used before, and I'm going to do that for each of them. So let's do lemon juice. So lemon juice, we've got our hydrogen ion concentration is 10 to the minus 2.3, which 10 to the minus 2.3, 3 negative shift 10. So that's 5.0 times 10 to the minus 3 moles per liter. For orange juice, it's 10 to the minus 3.3. So in that case, I get 5.0 times 10, so 3.3 negative shift log 10 to the minus 4 moles per liter. So if you take a look at these, what I can do is divide them. So we can take 5.0 times 10 to the minus 3, divided 5.0 times 10 to the minus 4, and that equals 10 times more concentrated. So hopefully you know that when you see these exponents that you know that 10 to the minus 3 is more concentrated than 10 to the minus 4. Remember, 10 to the minus 4 has an extra 0 and it's a little bit smaller. So taking a look at this question, so notice that a pH of 2.3 is 10 times more concentrated than a pH of 3.3. And that should make sense if you understand how the exponents work. That's a difference of 10 to the 1, and 10 to the 1 is of course 10, and 10 times more concentrated. So let's talk a little bit about measuring pH. You had a chance in Lab 1 to measure pH using the pH meter, and you also used the pH paper, the color strips, or the litmus paper is sometimes called. Of course, the pH colored paper just has indicator chemicals in it. And I have a slide actually coming up on indicator chemicals. And they change colors at different pHs, and you might use a different one for depending on what type of titration or whatever it is that you're looking for. You can also do a titration where you're adding something like sodium hydroxide to an acid, and in that case what you're doing is you're counting the number of moles of base that is reacting with that acid to figure out exactly how much is in that solution. So a pH meter is usually one of the best ways to do it. You're getting accurate numbers, and they're relatively easy to use. Here are some acid-base indicators, and there's a whole bunch out there. There's actually more than just this list, and you're going to use an indicator this week in the lab. I think it's called phenol red, and it goes from yellow to red, and so you're going to use that in this week's lab. So let's talk a little bit about acidity. And it says here why acidity is, of course, when we're talking about aqueous things, we're often talking about the concentration of hydrogen ions. But a more of a definition of acidity, of course, is the capacity to react with a strong base. So in water, acidity often has something to do with carbon dioxide. So you can see it says here, how is carbon dioxide acidic? So let's think about that. If you have carbon dioxide, so CO2 is carbon dioxide, it actually naturally reacts with water. So there's water, H2O, in an equilibrium. And in that equilibrium, we make something called carbonic acid. So carbonic acid is H2CO3. Carbonic acid. So carbonic acid will further dissociate, so H2CO3, and that breaks down into some hydrogen ions, so that's acid, plus bicarbonate, HCO3 negative, so that's bicarbonate. Bicarbonate will actually break down even more, and it will make carbonate. So here we go. So that's why carbon dioxide can add acid to water, and that's actually what you're going to do in tomorrow's lab. You're going to blow through a straw, and you're going to deliver some carbon dioxide to some water and make it slightly acidic. And you can do that by the carbon dioxide turning into carbonic acid and the carbonic acid dissociating. So you can see there's a question here. It says, what affects the levels of CO2 and O2? So CO2, we have cellular respiration. Cellular respiration is what makes carbon dioxide. Also, you could add the burning of fossil fuels, but both of those are pretty important environmentally. So cellular respiration will produce carbon dioxide. And of course, we have that other process called photosynthesis. And hopefully you know that photosynthesis will, of course, consume carbon dioxide. And it's the reverse for oxygen. So this is consumed by respiration. I'm just going to use an abbreviation here. And hopefully you know that this is produced by photosynthesis. So that is, those are some hints for tomorrow's lab. So let's talk a little bit more about acidity today, and then we'll come back next day and we'll talk about alkalinity as well. So it says here, why do we care? Well, like I said, water or acidity affects all sorts of different processes. You can see this note, for example, in the wastewater industry, we want it relatively acidic, and it makes the digestion process go a lot better. And all sorts of industries, you know, they're going to rely on different pHs. In many cases, they want water as neutral as possible to prevent corrosion of their equipment. And so, you know, this is something that's monitored carefully in many, many different types of industries. So sources of acid, of course, we've got carbon dioxide, which is from respiration and fossil fuels. And we also have acid rain as being a source of different types of acids. So acid rain is rain that has a pH of about 5.6 or less. And where does acid rain come from? It comes from all sorts of industrial processes. So we're looking at different types of sulfur dioxides and nitrogen oxides that are produced in industrial processes. They're released as air pollution. They react with water, and we make sulfuric acid and nitric acid. And then, of course, it rains on other places. And so if you're wondering, you know, where we are in Canada in terms of, you know, how sensitive we are, we're talking about, so the red is low sensitivity, because it's non-carbonate bedrock, but you can see that much of Alberta is high. So we're talking about lots of limestone and carbonate bedrock. So there's Alberta right there. And I'm not exactly sure what the levels of acid rain are in Alberta, but hopefully we can find out sometime this week and learn a little bit more about that. So this is where I'm going to finish off today, just a cute little cartoon. It says here the effects of acid snow, and you can see the little snowman has become a mutant. And, you know, so a little joke for you for one day. So I will see everybody next week, and I hope you have a great weekend.